Welcome to the lecture number 47. From today we are going to be second chapter, Pythagoras theorem. Since you all are studying this Pythagoras theorem right from 5th standard, easy to understand so far. You have learned the applications of Pythagoras theorem, but now we are going to study the proof. So first of all, we'll find this theorem is there, which is given on page number 33. Try to understand the statement of the theorem. In a right angle triangle, you will find triangle ABC is a right angle triangle. If the altitude is drawn to the hypotenuse, since in triangle ABC angle B is of 90 degree, we will find if altitude is drawn on hypotenuse is AC, then the two triangles form. Now here there is one triangle, here there is one triangle. The two triangles formed are similar to the original triangle and to each other also. So you will find because of this altitude BD, two triangles are formed, namely triangle ADB as well as triangle CDB. These two triangles are similar to each other, as well as ABD is similar to triangle ABC as well as DBC is also similar to triangle ABC. Is that clear? Now please try to understand the same result we have to prove. Now for example, if I am going to consider triangle ADB and triangle ABC. So in triangle ADB, in triangle ADB and triangle ABC. Trying to understand this triangle ADB, in which angle A is there. Angle A is angle of triangle ABC as well as angle A is also angle of triangle AB. Therefore, you will find angle A is congruent with angle A. Angle A is congruent with angle A. That is common. That is common. Now, if you see in triangle ADB, you will find angle D is of 90 degree. And if you see triangle ABC, this triangle, in which you will find both angle ABC is 90. So, therefore, you will be getting angle B is congruent with angle D. Reason is it is 90. It is 90. Therefore, triangle ADB similar to triangle ABC by a test. By a test. Very simple to understand this concept. Angle A is angle of triangle ABC as well as angle A is also angle of triangle ABD. Therefore, A is a common angle. Next to that, you will find angle ABC. The whole angle ABC, which is of 90 degree, is also congruent with angle D, which is also of 90 degree. So you will be getting angle D is congruent with angle B, which is 90 degree, and therefore triangle ADB similar to triangle ABC by a test. I am going to label this as result 1. Now we will find second triangle. I am going to prove now triangle CDB. Try to understand. Triangle CDB, in triangle CDB, in triangle CDB and triangle CBA. I have mentioned over here triangle CBA. The name of the triangle ABC, I have taken it as CBA. Try to understand the reason behind it. Because you will find angle C of triangle CDB, angle C of triangle CDB, as well as angle C of triangle ACB are common angles. So in this case, in the first case, we consider A as a common angle. Likewise, in the second case, what we will consider C as a common angle. So you will find here angle C is congruent with angle C, that is common. Angle C is congruent with angle C is common. Then you will get angle D. Angle D is congruent with angle B. It is 90. It is 90. Therefore, we will get triangle CDB similar to triangle CBA by AA test. By AA test. So this is our result number 2. This is our result number 2. So from result number 1 and 2, you will notice very easily ADB is similar to triangle ABC, correct? As well as CDB is similar to triangle CBA. But this is a common triangle. This is a common triangle. So, as per the requirement of our to prove condition, you will surely find triangle CDB as well as triangle ADB, both of them are similar to the original triangle, which is ABC. As well as, since we all know the property of transitivity, if one triangle is similar to the second triangle and second triangle is similar to the third triangle, then naturally first and third also become similar to each other. So therefore triangle ADB similar to triangle CDB similar to triangle ABC. So from 1 and 2 we draw a conclusion that triangles formed on both sides of the perpendicular are similar to each other, as well as each one of them is similar to the original triangle. That is what we have to prove over here. This theorem is asked very rarely in the examination, very rarely. So you don't have to bother much. But to understand this property is very, very important, because while solving sums, you will find many times we have to use this property. But very rarely this sum is asked in the examination. So you don't have to bother a lot about this theorem. Now next theorem is on the same page, which is very important for accommodating students. Theorem number 2. Here you will find PQR is triangle. Now this theorem, statement of the theorem, you see. Theorem statement is in right angle triangle, in a right angle triangle, perpendicular drawn, perpendicular drawn, perpendicular drawn on hypotenuse, perpendicular drawn on hypotenuse is the geometric mean. I am not going to write too much in here. Is the geometric mean is the geometric mean of the segments into which hypotenuse is divided, into which hypotenuse is divided. Then you will notice over here proof. Okay, before that, to prove that, I will not give now much things. Given and all, given is very simple. QS is perpendicular on P1. And to prove that QS square is equal to RS into PS. Okay, dear students, this is called as geometric mean theorem. Very important property by that way, because this property we use for solving many sums. Okay, fine. Please try to understand. Statement first. In a right angle triangle, now you find triangle R2P or PQR is a right angle triangle. Perpendicular is drawn on hypotenuse. So QS is a perpendicular which is drawn on hypotenuse PR. Okay. Then is the geometric mean. You all have studied in algebra what is the meaning of geometric mean. The square of the term which is geometric mean. So you will find that since we have stated over here QS is a geometric mean, therefore you have to take QS square. But this is a geometric mean of what? The parts of the segment PR. The parts of the segment PR. Now, because of this QS perpendicular drawn on PR, we have got two parts of the segment PR. One is RS and other one is PS. So what we have to do? RS into PS. Now, this technique you have to use while solving many sums. Whenever you draw a perpendicular, this angle is congruent with this. So you have to show them with identical marks. In the same manner, you will find if perpendicular is drawn, then this angle, namely angle RQS, is congruent with angle. So this marking is very important, that you draw a perpendicular on its side. You take, supposing if you take cross, on the other side you have to take cross. If you take over here this sign or this symbol, the same. then it becomes very easy. If you remember these things, then it becomes very easy. So in proof you will find, I will write this way: triangle RQS. Triangle RQS is similar to triangle. Now please see the analytical marking. I am going to write the name of these two triangles. I am going to take these two triangles similar, which we have already studied in the previous theorem only, that whenever perpendicular is drawn on the hypotenuse, triangles formed on both the sides of this perpendicular are similar to each other, same property. So you will find, if I write the name as RQS, so this angle is congruent with what? This angle. And this triangle's name should begin with Q, because R and Q should come at the same position. So Q, we have to maintain the sequence of 1 1 correspondence. So we'll find Q, okay, like this. So cross is there. Here also there is a cross. So QPS, triangle QPS, by perpendicular hypotenuse L. In very short form, I have mentioned the name of the previous theorem, that perpendicular hypotenuse. Okay, if you write the names of the triangles in this very appropriate way, the next part becomes very easy. Next part is very easy. Taking the ratio RQ upon PQ, that is equal to QS upon PS. QS upon PS, that is equal to RS upon QS. RS upon QS. First let us from here. QS, PS is here. The first and the last, here also first and last. Fine. The next step is, what result we need? QS square. So to get QS square, we can equate these two ratios, because our aim is to get QS square. Of course, these two triangles are similar, these ratios are equal, corresponding sides of similar triangles, all this is correct. Then QS upon PS, therefore QS upon PS is equal to RS upon QS. RS upon QS, same ratio, same ratio. Then QS into QS will give us QS square. So QS square is equal to RS into PS. That is what we have to do. QS square is equal to RS into PS. So you will find that perpendicular is a geometric mean of the parts of the hypotenuse, because you will find, because of QS, two parts formed, namely RS and PS. So QS square is equal to RS into PS. This theorem's proof they never ask. So far, proof is not asked in any one of the examination. But only the important thing is what? Property, because we have to use this property many times. Now let's do the next theorem, which is very important and which is likely to come in examination also. That is Pythagoras theorem itself. Pythagoras Statement in a right angle triangle. Statement in a right angle triangle, the square of the hypotenuse in the right angle triangle in the right angle triangle, the square of the hypotenuse, the square of the hypotenuse square of the hypotenuse is equal to the sum of the squares, is equal to the sum of the squares of the remaining sides. This theorem you are applying right from your lower classes many times. First time you will come to know the proof of this. So triangle ABC is given. Triangle ABC this is required figure. Triangle ABC is given, in which angle B is of 90 degree. So we will find given in triangle ABC, angle B is of 90 degree. Triangle ABC, angle B is of 90 degree. You all know hypotenuse square. To prove that AC square is equal to AB square plus BC square. So sum of the square of the hypotenuse. So AC is hypotenuse. Square of that is AC square is equal to sum of the squares. Sum is addition of side AB and BC. So AB square plus BC square. Now I am going to do a construction. Construction is here. Construction is draw BD. I am going to draw BD. So draw BD. Perpendicular on AC. Okay, draw BD perpendicular on AC. Now proof as usual. You all have studied in the first set that the triangles formed on both sides of this perpendicular are similar to each other, as well as each one of them is similar to original triangle. That is very important. we are going to use the same fact that whichever the triangles are formed here, this is one, this is another, and both these triangles are similar to the original triangle. So here in this case you will find triangle ABC, triangle ABC, and triangle ABC, and if I take ABC, I must write it as ABB and triangle ABB. Triangle ABC and triangle ABB, they are similar to each other. Okay? So in this case, we have to write only the reason that hypotenuse side here when I write this in very short form, I am not going to write in too much in detail. Okay. So I was simply verifying whether there is a need to prove that A is congruent with A, B is congruent with C. No need. You can directly take it and write here hypotenuse side theorem. And once triangles become similar, you all know, if triangles become similar, then ratio of their corresponding sides are equal. So that word corresponding is important. So AB upon AD, that is equal to BC upon DB, that is equal to AC upon AD. Corresponding sides of similar triangles. Corresponding sides of similar triangles. Now you will find in our required result, we need to get AB square. What we need to get? AB square. And if you look at these all ratios, you will surely find, if I equate first and last, AB upon AD is equal to AC upon AD. Then AB square is equal to AC into AD. This is our result number 1. Very simple. Because you will find if I equate first and the last one, then you will surely get AB into AB, that is AB square, is equal to AB into AC. Clear? Then you will find likewise in the same way triangle ABC similar to triangle. Now this time I am going to take triangle DBC for similarity. So angle C is a common. So here also B is 90 in ABC, B is 90. So here T is 90. So I write T over here. Right? So BD is same way we are students. Reason is same, hypotenuse side here. Hypotenuse side. Hypotenuse side there. Now I will take a ratio AB upon BD. AB upon BD, that is equal to AB upon BD is equal to BC upon BC. BC upon BC, that is equal to AC upon BC. AC upon BC. Corresponding sides of similar triangles. Corresponding sides of similar triangles. AB upon BD. BC upon DC is equal to AC upon BC. What important precaution you are supposed to take is this 1-1 correspondence to maintain in very proper order. Otherwise all things will go wrong. Okay, now let's see here. In final result we want AB square plus BC square. And usually find if you equate these two ratios, BC upon DC is equal to AC upon DC. If you equate these two ratios, then you will be getting BC square is equal to AC into DC. Then you will be getting BC square is equal to AC into DC. This is our equation number 2. This is our equation number 2. But if you look at the required result here, to prove that AC square is equal to AB square plus BC square, we have already got AB square, value of AB square, we already got value of BC square. So naturally our next step is to add in equations 1 and 2. So AB square plus BC square. So adding equations 1 and 2. This is important theorem, dear students. Very important theorem, because its proof can be asked in the examination. Okay, so adding 1 and 2. Adding 1 and 2. When we add 1 and 2, left hand side of 1 plus left hand side of 2. So AB square plus BC square. That is equal to right hand side is AC into AD. AC plus AC into DC, AC into DC. So this is how you will find. We have added the left hand sides, AB square plus BC square. We also add the right hand sides of equation 1 and 2, and we got this space. Now very interestingly you will notice that AC is a common, because these two groups are separated by plus sign. So if you take AC as a common, from first as well as from second group, you left with AD plus BC. If you take AC as a common, then you left with AD from here. And if you add AD plus DC on the figure, you will find if you add AD plus DC, you will be getting AC. These are common later. Okay, if figure is not there in front of me, I can say these are common later. So you will find AD plus DC is AC. That will give us AC square. So AB square plus BC square is equal to AC square, or required result is AC square is equal to AB square plus BC square. So from examination point of view also, dear students, this is very important theorem, that theorem of Pythagoras. And you must be happy also to know this. This is important reason being that very easy proof to write. It's not so difficult to understand all these concepts. Only that one correspondence is important. Okay. So I think I should stop over here. So in the next lecture, that is lecture number 48, I'll do the next theorem, which is very important also, but very rarely asked in the examination. That is converse of Pythagoras theorem. And especially this year, you are going to study a very new theorem, which is called as Apollonius theorem. The proof of Apollonius theorem is a little bit difficult to understand also, as well as to apply also. Okay. So this is how you will find very important theorem, Pythagoras theorem. We have finished. In the next lecture, I will be teaching you the converse of Pythagoras theorem. In addition to that, we will do very important theorem, that is Apollonius theorem. So that's all over here for this lecture number 47. Thank you very much, dear students.